In this example, we're going to imagine that we have some telemetry from a rocket that's just been launched, and we know at 10-second intervals from the launch the value of the velocity in feet per second. We're going to try to figure out the total distance traveled by the rocket during the first 80 seconds. Now we know that there are no changes of direction or anything like this, and so the distance should just be the same as the displacement, and it should be equal to the integral of the velocity over the interval in question, which is from time 0 to time 80. Now the question is, how do we do this if all we have are values from a table? One possibility would be to try to make some sort of model. We could graph them, we could try to see what the form of the model was, we could try to make one, and then we could do the calculus thing to that model. But it turns out there's a more direct method that we can take, and that involves just using the values themselves and applying some of the approximation techniques that we've been talking about. This is particularly easy if the subintervals are equal in width as they are in this case, because we have some formulas that we derived with that idea in mind. If they weren't of equal widths, there'd be some more work to do, and that's the thing that we'll actually look at in the run-up to the AP exam, because that's the thing they sometimes ask about. But suppose we wanted to make a left endpoint estimate of the integral from 0 to 80 of this velocity. We've got a bunch of values of the function. It shouldn't be all that tough. So we've got 1, 2, 3, 4, 5, 6, 7, 8 subintervals, and the number of subintervals ought to be always one less than the number of ordered pairs that you have. So I'm going to have B minus A over N times basically the function values that represent left endpoints, so all but the very last one. So I've got 5 plus 14 plus 22 plus 29 plus 35 plus 40 plus 44 plus 47, not 49 because it's not a left endpoint. And if we do the arithmetic, we find that this is 2,360 feet. And that would be an underestimate, an overestimate, increasing function. I'm going to say the left endpoint estimate is an underestimate. Right endpoint estimate, B minus A over N, 80 minus 0 all over 8. Everything that's a right endpoint, so basically we just knock out the 5 and we include the 49. So we've got 14 plus 22 plus 29 plus 35 plus 40 plus 44 plus 47 plus 49. And that should be a greater value, and in fact it is. It's 2,800 feet. And if we can assume that the velocity is increasing over all of the subintervals as well as just from one 10-second value to the next, then we should be able to have fairly high confidence that the actual distance traveled is somewhere between these two numbers. But we can make a midpoint estimate. Although making a midpoint estimate gets a little bit tricky when you're given data values, because not everything is the value of a midpoint. I can't know the value at the midpoint of the subinterval from 0 to 10 because I got nothing. So if I'm going to use midpoints in a situation like this, I have to sort of use two at a time. I have to say to myself, here's the interval from 0 to 20, and I know what's going on at that midpoint. And then here's the interval from 20 to 40, and I know what's going on at that midpoint. And then from 40 to 60, there's that midpoint, and from 60 to 80, there's that midpoint. So there's something a little bit unsatisfying about using midpoints in this context, because we have information that we're leaving on the table. We're only going to be using information about 4 of our 9 ordered pairs, but that's just how it's going to have to be if we're going to make a midpoint estimate. So B minus A is still 80 minus 0, but we now have only 4 subintervals, right? So they're twice as wide, and we're looking at the midpoints. And so the values at the midpoints are 14, 29, 40, and 47. And if you do the arithmetic there, you're going to get 2,600 feet. And at least it has the virtue of being somewhere between the left and right endpoint estimates, and so maybe that gives it some credence. But it is a little unsatisfying to leave all that information on the table. Then trapezoids. How's that going to look? Well, that's B minus A over 2n. So we're going to have 2 times the 8 subintervals, because we're back to using all of our information. And what goes here in the sum is all of these values, everything but the first and last multiplied by 2. So we are going to have 5 plus 2 times 14 plus 2 times 22 plus 2 times 29 plus 2 times 35 plus 2 times 40 plus 2 times 44 plus 2 times 47 plus 49. I hope I didn't miss any. And if we do the arithmetic, we get about 2,587 feet. So without having any idea what the function might be that would govern these velocities at these times, we nonetheless are able to use our estimation procedures for integral estimation to get a fairly decent estimate of how far the rocket has traveled. You tell me, somewhere in the neighborhood of 2,600 feet. We'll see in the near future a method that allows us to get a somewhat more refined estimate, and this is not 2587, this is 2580.